in this lecture, we're going to be looking at what is metabolism, ATP and NADH, laws of thermodynamics, and oxidation reduction. So this class is actually central to biochemistry and to the rest of the lectures. And what you want to know is, again, that the lectures are the focus. All of the complete figures are in your textbook. You have heavy memorizing. I would focus you exactly on what you need to memorize. It's not like you're going to be memorizing every pathway. More about understanding, but I'm not going to lie to you, there is memorization. And then you definitely want to do these problems every single time. You want to catch up with the problem. So look at the lecture, reinforce it with that part of the book, and do the problem sets. And then the examples I will post on the B courses of the exam, so you have a feeling for the level of depth. And then in lecture, I'm also going to be doing some more fun things like videos or other examples, trying to make it as interesting as possible. Okay. So we start really simply, and you see a slide like this, and it's really seems pretty boring, but all of these slides have a depth to them. So if you think about like the evolution of our life system on Earth, right, we have photosynthetic autotrophs and heterotrophs. So auto, right, is self, and troph is like basically feed. So it's self-feeding. It's being able to get everything it needs from CO2 from the air. It doesn't need anything else. And heterotroph would be hetero, so it needs something from outside. So in this case, can somebody tell me what the photosynthetic autotrophs are producing for the heterotrophs? Yeah. Right, so they're producing oxygen, which goes here. And this we should all know at this point, but you're going to learn more about this. You probably had some in Bio 1A as well, but you're going to learn more about it in terms of the metabolic cost and also electron transfer. They also produce organic products, right? So they're producing actually the amino acids, a lot of the vitamins, the cofactors that the heterotrophs then need. And what about the heterotrophs? What are they supplying? I'm going to go to someone else. Whoever, you can just raise your hands. Yeah.
CO2 and H2O.
Right. So they're producing CO2, I think I have on the bottom, and then H2O actually at the very bottom. So I think people usually think about this part, but they don't actually think about this part, right? So that you're actually exhaling CO2, and then that's important for this cycle. Okay. And typically when we're thinking about this, right, we have, this is what I was talking about with self-nourishment with CO2 and heterotrophs, right, having nourishment from others, which they have this organic carbon products. And then what you want to think about are what these organisms are. So plants, algae, photosynthetic bacteria. And then on the other hand, right, we have the consumers, which are animals and also some bacteria. So this is a very simple slide, but it guides life on this quick. So if we move forward to the basis of this course, which is metabolism, right, we're talking about the reactions that make up life. And there are two major ways to look at these, which are anabolic and catabolic. So anabolism is synthesis. So you're taking something that's simpler and you're making it more complex. And whenever you're doing that, you're putting in chemical energy, like ATP or NADH. These are reductants, FADH2. And then you're creating something more complex. So you're using chemical energy or electrons to make something that's more complex. That's anabolism. And catabolism is degradation. And again, here you have the opposite, right? So you're breaking down. And when you're breaking down, you're actually releasing chemical energy. So we have synthesis and we have degradation. We're going to spend this lecture talking about these key products that help catalyze synthesis and that are released in terms of when you catabolize. So these are central to the coupling of synthesis and degradation. And these are, again, ATP and these NADH and FADH2. So we're talking about chemical transformations. I'm just trying to say everything a couple times because sometimes you say something a slightly different way and that one person, it helps them with it. So basically, metabolism is the summary of anabolism, synthesis, and catabolism, degradation. And so it is all of those. And all of these are catalyzed in biological systems by, I shouldn't say all, but most of this is catalyzed by enzymes. So the first thing we're going to look at is ATP. And you'll see this drawn a number of different ways in your textbook. I'm using actually the picture that was from 1-26, not the one that's in chapter 13. I think it's a little bit easier to look at. So in this case, maybe I already used it up. So the top structure is ATP. You definitely want to know that structure. So I would just practice drawing that structure. And then where I have the arrows are actually the phosphoanhydride bonds. So those are like connecting the different phosphate groups. And then you have the adenine, and then you have the sugar group making it adenosine. So all of you are familiar with that type of nomenclature from the first part of the class, correct? Yeah, okay. So a nice way of displaying it is to just have the circles. So whenever you see a circle with a P, it actually is standing for phosphate, inorganic phosphate. And I'm sorry that my finger is longer to reach because this is worn out. But so if you have adenosine triphosphate, you have 3 P's that are circled, right? And then you can have a reaction where you cleave off one phosphate. So we could write it as a P with a circle, we could write it as inorganic phosphate, the chemical structure, or we could write it as PI. Did Professor Callender also talk about PI as PI? Okay. So those are just the different ways that biochemists and chemists talk about phosphate. And then pyrophosphate is basically when you have 2 of them together. And again, you could show 2 P's with a circle, you could actually draw out the chemical structure, or you could have PPI for pyrophosphate. So whenever you cleave, right, depending on if you cleave one phosphate, what you get left is adenosine diphosphate, right? 2 phosphates are left, and I'm really sorry this isn't working. And then if you cleave off 2 of them, right, you get 1 remaining, so it's adenosine monophosphate. And you can also transfer the whole adenosine so basically you can also have another reaction which we're not focusing on, but the book talks about a little called adenylation, where you're actually adding this full group to a molecule. So when we're talking about ATP, we're really talking about the transfer of phosphoryl groups. It's not so much about energy from hydrolysis, but it's actually transferring these groups onto proteins or onto other substrates, and we'll show examples of this in a minute. Another way, right, that we're actually catalyzing reactions, I'm not going to use the word catalyzing, facilitating reactions is actually by using molecules that facilitate electron transfer and can act as electron carriers. So NAD is one of those molecules. And again, you should get used to recognizing structures, so if you ever have to draw something, you know, right, each part of it. So again, you have the adenine, here you have the sugar group, and then you have the phosphate, right? So you have adenine, in this case dinucleotide, and then at the very top is the nicotinamide actually, it's that structure. So NAD plus is the oxidized form, and it's a little bit complicated because usually when we talk about something being like, let's say Cu2 plus, right, that's the charge on copper, on Cu. But here, they're actually using NAD plus to illustrate that it's in its oxidized form. So it's not the charge on the whole molecule, it's just the charge on this nitrogen right here. In purple, the purple one. Maybe I can use my pointer. There, yeah, right there. That's better. So if you look at this structure, right, it actually has a negative charge. So whenever you see NADH or NADPH, it's different. And this is, again, one of those things that's like an exemption to the rule type of thing, like we have in the English language. This is just makes it easier for people to figure out if it's in the reduced or oxidized form. So it's all about this N right here. So right now, this is the oxidized form, and before we move on to reduction, I just want to talk about NADPH, and the only difference here is that you'll have a phosphate group here. So what about reduction? So basically, for my class, you don't have to know about the hydride atom and exactly how this happens, but you just have to know basically what the different forms are. So in this case, trying to move the arrow, you have 2 electrons coming in with the hydrogen, and basically what they're doing is it's forming a hydrogen bond here. And whenever you have, so when you form this form of it, the reduced form, NADH, there could be 2 positions, and this is not important to the class, I just want to say it once so that you know if you see it in the future. So this is the type of thing where the hydrogen, right, can be in 2 planes, right, the front or the back. They call it A or B in the book. And because NAD is often associated with particular enzymes and particular reactions, enzymes can favor one form or the other, the A form or the B form. But this is a detail that you don't need to know for exams and things, I'm just letting you know. So enzymes have evolved over long periods of time, and so there could be reasons for that specificity in terms of a particular A or B form can catalyze one enzyme reaction versus another, but it's not critical in terms of what you need to know for the class. I might answer in a second, I don't know. So, sorry, just one. So this is, I just wanted to point out the phosphorus hydride bond. And then the plus, I'm just re-emphasizing, right, goes to the amide oxidation state. And then I wanted to mention one more thing, which is the dominant form in the cells. So in the cells, the dominant form of NADPH is, I just said it, NADPH, the reducing agent. And in the NAD, it's actually NAD+. So if we think about the first overhead that I showed you, right? So let's go back. Not one of the very first. In the cell, so NADPH is mostly involved in synthesis. And in the cell, the concentrations are such that NADPH is very high, and it's usually involved in synthesis, whereas NAD+ is the dominant form of NAD and NADH, and so it's typically involved in catabolism. Do you still want that question? Yeah. Okay.
I can see how the form of series
Yeah, so it just has to do with, I mean, this is not like my area of expertise, so I'll just say that, but the understanding is because of the planar structure of it, it's able to go, the one that comes in can be in the front versus back, versus the one that was already there can be in the front or the back. So for example, maybe a good way to say this is, because in biological reactions, you would be adding an H, so, I have to use my arrow. Yeah. So, if let's say you had this was like a deuterated hydrogen that you could follow, right? In the A, you would have it here, and then in the B form, it would be here. Okay? Did that help explain it? Okay. Yeah. So feel free to ask a question, just like that, if the way that I'm saying it isn't quite working with the way you were taught before. All right. All right, so let's look at another molecule, FAD. So this is flavine, la la la. I don't know if you're gonna say it right now. Flavin adenine dinucleotide. So again, whenever you're looking at these molecules, like think about what they are, because it's also, I used to dance for many years, and you know, when you're, or doing any sport, right? When you're first learning the moves, right? Each move you have to learn, and then you start being able to put it together and you don't even have to think about it, right? Same thing here. So again, here we know now, we know what our adenine looks like, we know what our sugar looks like to get the nucleoside. It's with a phosphate, so it's a nucleotide. Same thing up here, they're just displaying it differently, right? So we actually have the flavin adenine dinucleotide, and this is the flavin part of it, okay, this nice ring structure. And again, the thing similar to the NAD and NADP is that you can actually, this is the oxidized form, and then we can add electrons to reduce it. And the first reduction is here. So you would want to, if I gave you these structures, you'd want to be able to tell me where this would go and draw this. And then the second one is actually adding right here, and that's fully reduced. So sometimes the intermediate in something like this is not stable, but in this case, actually, you can get this semiquinone as a stable molecule. So you can observe both forms. So now we're moving into what governs basically all of metabolism, which is bioenergetics and thermodynamics. So what is bioenergetics? So it's the quantitative study of energy transformation, and then thermodynamics are the basic laws that govern our processes. So the first one, again, they sound simple, but they're quite profound when you're working on them. So the first one is conservation of energy. So it can change form, it can be transported, but it cannot be created or destroyed. And then entropy, which is basically, in all processes, entropy increases. So that's the randomness or disorder. So for those of you that are artists, one thing to think about for the conservation of energy is that sometimes people are looking at something and they're like, well, within this beaker, it doesn't seem like energy is conserved. And that's because they're just looking at the beaker, not at the entire system, right? So I think of it similarly for an artist. An artist can make a painting, but really your experience of the art is where that painting is displayed with respect to its environment. And so it's really more of an open system. It's even more obvious in what we're talking about in chemistry, because heat can be dissipated, energy can be transferred to things outside of our beaker, but it's just a nice, I like to give you different examples so that one might resonate with you. So basically we have conservation of energy that's always taking place, and we have entropy is always increasing. So now we get to the fun part of like figuring out how you actually calculate this and think about it. So the way to calculate energy is this reaction, the Gibbs free energy equation. So you will need to know this by heart, and hopefully you'll integrate it into your DNA, into your memory storage, and use it regularly. So delta G is the Gibbs free energy. It's what tells you if a reaction is going to happen. There's the arrow. Okay, delta H is the change in enthalpy, so that is usually thought of as heat, right? Is it producing heat? Is it actually taking up heat? Does it use heat? T is the absolute temperature, so that's in Kelvin. So that's, right, always plus 298. Plus 273, so 298 is 25 plus 273. And delta S is the change in entropy. So whenever you see the delta, it's change, and then G is Gibbs free energy, H is enthalpy or heat. You can think of H for heat, T is temperature in Kelvin, and then S is for the change in entropy. So when delta G is negative, it's exergonic, and that means that it's actually, that reaction is going to occur. And when delta G is positive, it's endergonic and the reaction should not occur spontaneously. A couple things, we're going to be going through all of this and you're going to get lots of examples, but the standard free energy is this, delta G0, and that's the reaction at 1 molar, and this was defined by chemists. Okay? But we're biologists for this class, this is biochemistry, so we actually want to talk about this as relevant to biological systems. So the reaction is always at pH 7 and at 25 degrees Celsius. Now, you might be looking at something that's not happening at pH 7 and not happening at 25 degrees Celsius, and then you need to adjust it. And we're going to learn more about also what's assumed about the concentrations as well. So you always want to make sure that you're looking at the delta G prime, and you know that that's defined in this way. So this is the way we're defining it across the world. So I'm just reiterating this. The delta G is the energy. It's the energy to do work. So if it's negative, it can go forward and the energy is released. And if it's positive, then it takes energy to occur and it can't. So this might be anti-intuitive, you just have to remember it. You always want delta G to be negative for the reaction to occur. And once you go through the equations, then you realize like it does have to be negative. And the reactions are also always at 1 molar. Okay. So we relate delta G to the reaction in a number of ways. This is one of the standard ways that it's related, and you're going to need to know this and use this. So if you have a reaction where you have A plus B goes to C plus D, you have the K equilibrium as the concentration of the reactants over the products. And then when you look at that and you're trying to calculate your delta G0 prime, this is a formula that you'll be memorizing. It's minus R, which is a constant, T, the temperature in Kelvin, natural log of K prime equilibrium. So, and this is K prime equilibrium. So what it's telling you is that for any particular situation, whether that reaction is going to occur, right, we want it to be negative, also is dependent on the concentration of the reactants. And we're going to relate this to metabolic pathways. So, for example, right, if you want this to be negative, and if you have, you know what, I'm going to talk about it in another slide. I'm going to wait for this one. So let's go through this example. So here we have K equilibrium is equal to the products, ADP, phosphate, over the reactants, ATP. In biological systems, you usually leave out water because most things are happening in an aqueous environment. So that, again, can be different from how some of you who are chemists or chemical engineers might have learned this. So then what you do is you plug in your information, right? So if you were solving for this, you would have R, which is a constant, and that's the constant value. You would have your temperature in Kelvin, 25 plus 273, and then you would have the natural log of the K equilibrium constant, which is right there. And this is negative. So in this case, right, the reaction would be favored. And this is assuming, though, that the concentration of everything is at 1 molar. And I mean, that's not probably going to happen in the cell very often, right? Usually things are at very different concentrations. So now we need an equation that relates what's really happening in the cell at pH 7, at the right temperature, but also at the right concentration. So when we look at K equilibrium, so if I show a table, you definitely want to be going back to that. This is just the point that the concentration of so you're always thinking products over reactants. Like, so this is 1,000, right? 1,000-fold higher in terms of the products over reactants, right? And this is very low. And so here, right, you're going to be moving forward, and here you're not. So So the major thing I wanted to point out is that here you have like a 1,000-fold change, and here you only have a 2-fold difference. So you'll have a huge difference that you need in the change of concentrations to get a small difference in the delta G. Okay. And this just relates back to the formula. So let's actually plug in some stuff. So if we look at this example, we have glucose plus phosphate going to glucose 6-phosphate plus water, and then ATP plus water going to ADP plus water. And this is the final reaction, but it's actually in these two parts, and you'll see why in a minute. So the first reaction, I'm actually just going to put that in for you. The delta G, so you can look this up. There's a table in your book that has this information. I think it's 13.6, but you guys can double check. Right, so you look up the delta G0 and it's 13.8. And then you look up the delta G0 for this reaction and it's minus 30. And so this is one of the tricks that biology uses in order to catalyze reactions, is it couples a reaction to the transfer of a phosphoryl group to drive the energy in a favorable way. And so what you're seeing now is if you add these together, you now have a favorable net reaction, right? So the reason I can add these together is because the phosphates, the intermediates, are the same. And then the water we don't care so much about, but again, the water is canceling out as well. So we have ATP providing energy by group transfer, and it's particularly that phosphoryl group transfer. So just like when we're calculating what's going on, right, we have talked about this delta G, the actual free energy, and the standard free energy. So the delta G for any reaction is in that, I shouldn't say for any, for a subset is shown in your table, in your textbook. And that's always the same, right, because it's defined as 1 molar, 25 degrees Celsius, and pH 7, but again, we're not operating at those conditions, so you have to adjust for your operating conditions. So the actual free energy is delta G prime, right? It no longer has that for being standard. So when you're taking a test or doing your problems, it might seem trivial, but this could be the difference between you getting a problem right or wrong. So you want to be really careful, right, to actually make a note of whether it's standard or whether it's the actual. So the actual is equal to the standard, which does not change. We look it up in a book, in a table, plus R, right, times the temperature. So this is a constant, times the temperature in Kelvin, times the natural log of the products over the reactants. And if all the concentrations are 1, then delta G is equal to delta G prime, delta G0. This should say delta G prime is equal to delta G0, right? So in that case, right, if each of these are 1, 1, 1, 1, 1, this whole thing, this whole term cancels out, and you have this is equal to this, right? And if you're ever like in math, right, doing a proof, you always want to check that, right? You're checking your assumption of how we're defining delta G prime. So in actuality, in the cell, this is what we care about, delta G prime, and that decides the spontaneity of the reaction. So if we have this situation like we looked at before, we already know that it should be favorable under standard conditions, right? But we haven't looked at whether like normal conditions. So now I'm giving you normal conditions, 0.5, 0.1, 50, and 1.2. And so we plug it in here, right? So we have, so what should go here, first of all? What's the delta G prime? The standard. I guess raise your hand up just because it's such a big class. Anyone? No, I have no one. Oh, yeah.
Negative 16.7.
Right. So it's negative 16.7. So that's going to go here for your delta G prime, 0 prime. And then here, right, we have the constant times the temperature times the natural log of right? The 50, 1.2, 0.5, and 0.1. And so then we add these together, and we'll get our final delta G, right? So when we add these together, now we see, wow, this is not going to occur spontaneously, right? Now later in the class, pretty soon, because the class moves quickly, you'll see that this is based on the chemistry. We haven't yet put enzymes into the equation. But this is really important in terms of thinking about how a reaction will proceed. So I guess we're going to try this again. See how I do. Okay.
Oh, okay.
So let me just start it.
E.
E? Mm-hmm. There you go, homie. Sure, it's E.
What? They have the same intermediate, so they cancel out in the equation.
I know you want A. I know you want A.
Okay. You got Sue thinking.
I don't know what that means. The free energy change.
Additive only.
Yeah, because these cancel out. So you only end up with the glucose and ADP.
Which one's cancel out?
The intermediates on both sides. That's what I'm saying. Yeah, that's what we're thinking. Or that's what I'm thinking.
E. Is mine on? Oh, then that's on. Homie.
Has everyone answered? Okay.
Wait,
Final
no.
answers.
E?
I'm gonna stop it. Final answers? Okay. So now let's see if I can do this. So stop and then show. Alright. I'm sorry I'm spousing against the learning. Let's see. Oh, there. Okay, so now I drag it. There you go. Yay! So,
Hey, Carlos.
You get the next one.
I still don't know what's
I
going
don't-
on.
It's like redox reaction. Did you ever do this?
The right answer.
The kinetic
They were
energy,
paying
and
attention and got
you
it.
only look at the
This is
constants,
really
so the
useful to
intermediates
me,
cancel out.
Because if, for
Like
example,
on the side. These
so
cancel
very
out.
few people do
Oh.
look at
And
the
then you only end up with the glucose, the
and see
ATP
why,
energy.
if you didn't get the right answer, you're gonna wanna like go back over this, maybe talk to your GSIs, you can come ask me afterwards. Also, sometimes it may be the way I explain something. So let's say we have a case where only 50% get the right answer, that's on me, right? If it's 90%, I think that this part, it just tells you in the audience, if you were one of these people that you wanna look at it.
Wait, so
a
what-
little
so
bit
these
more
cancel out?
closely, talk to your neighbors
phosphates, right?
more.
Yeah, so you only
and we can talk
calculate the
after
glucose to
class.
glucose energy and the ATP to ADP. So you get the overall energy.
We went a little bit more
intermediates.
slowly with things,
Cancel out, yeah.
Intermediates
we'll
are
just
water
have to
and
pick up
phosphate?
Next lecture. So,
Wes, Christy. Christy, go over this. See, this is the one I'm talking about.
You looked it up.
That's the key one.
Oh, it's on your playlist.